So now we'll start on something totally new. We're going to start thinking like a molecule here. And so this is going to be our introduction to what's called kinetic theory, and that's going to allow us to talk more about temperature and heat.
So we're going to start with what's called the kinetic theory of gas. Um, and basically, the kinetic theory tells us that molecules are constantly in motion and they move in random directions. And this is true not just for gases, but also for liquids and solids. So each molecule has a velocity and a kinetic energy. Um, and those uh, velocities are literally random. So in a fluid that's standing still, you'll have molecules moving in all sorts of different directions and moving very quickly in different directions. But when you add a whole bunch of molecules together, the random motion becomes predictable. So what we see is a sort of statistical average of the motion of the molecules. But on a random level, on a molecular level, it would be impossible to predict the movement of any one molecule. Um, why are we going to talk about this? Because it gives us a way to understand what's happening in gases and fluids. Um, we can understand important things like pressure and temperature and density by looking at what's happening at the molecular level. So that's what we'll do today. We'll start off with the idea of phase. And so we have different kinds of phases, and you all know this. We have, I don't even know what that is. It looks like a clamshell, but I think it's actually a rock. So that's a solid and a liquid and a gas. And here you can see a sort of picture of what those, um, a schematic of what the molecular, what's happening at the molecular level. For a solid, you have what's called a lattice of molecules. And so they're all connected by, not by little springs, but by what are called intermolecular forces. Those are both repulsive and attractive, and so the distance between the molecules is controlled by those intermolecular forces. They're still moving though, right? So they're sort of jostling about in there, and so they have some kinetic energy even within the lattice system. In a liquid, the strength of those intermolecular forces isn't strong enough to contain the kinetic energy of the molecules, and so the molecules start sliding around. They're still connected intermolecularly, right? They're not getting super far away. They're sliding past each other though, and they're changing position all the time. For a gas, the kinetic energy gets even bigger and it fully breaks away from those intermolecular forces. So in a gas, the molecules are far enough away that these intermolecular forces no longer have a significant effect on them, and they can fly off in all sorts of random directions. So we know from our own experience that temperature changes phase, right? If we heat up ice, it melts. And so it's not surprising that temperature becomes important when we start thinking about kinetic theory. Temperature, in fact, is, as it states here, an indirect measure of the kinetic energy of the atomic particles of a material. Okay, so as you heat up something, you're increasing the kinetic energy. And as we saw on the previous slide, if you increase the kinetic energy, the molecules have enough energy to break away or to loosen those intermolecular bonds, which is why you move from a solid to a liquid, for instance. The kinetic energy overcomes those bonds. So we have a couple of different ways to measure temperature. We have conventional scales, what we use when we talk about how warm it is outside, Fahrenheit and Celsius. And then we have the scientific Kelvin scale, which is an absolute scale. So what does that mean, an absolute scale? It means that at zero, when you have 0 degrees Kelvin or 0 Kelvin, you actually have no thermal energy. That is, the molecules are not moving. They have no kinetic energy. Remember, temperature is a measure of the kinetic energy of those particles. So in an absolute scale, if you have a 0, there is no kinetic energy in the material. And we can convert between those scales by using equations like this, and we can move between all three of these that are listed up here using that. But the big one to remember is for us is that Celsius is going to be about 273 degrees less than a Kelvin measurement. So if it's 20 degrees Celsius in a particular material, it's 293 Kelvin. Okay, so let's talk a little bit about what that temperature difference means and how that affects the material. So let's start with a solid material like ice, and we're going to put it in a closed container, and it's going to be partially filled with ice. And so above the ice, there's going to be a vacuum. That is a space with no molecules. Now, the ice's molecules are vibrating away because they have some thermal energy, right? They're not at 0 Kelvin. They're just below 0 Celsius. But these vibrations are contained by intermolecular forces. Now, there is something called sublimation, where some of these molecules are actually going to vibrate strongly enough away to escape the lattice, the lattice of the solid here and go into that vacuum. And that's called sublimation, when something goes from a solid directly to a gas without becoming a liquid. But for the most part, they're going to stay in that solid form. But as we heat the ice, the molecules are going to gain kinetic energy. They're going to vibrate more vigorously against those intermolecular forces, and they're going to start to overwhelm them and to slide past one another. Okay? But it's not going to fill the container, right? They're not going to break away from the other molecules. They're simply going to start moving around, okay? That's why fluid is fluid. That's why it can slide around while solid stays the same, because those intermolecular forces are they're attractive enough to hold the molecules close to one another, but not strong enough to hold them in place. Now, what happens when we add even more heat? Well, when you add even more heat, more kinetic energy gets added to those molecules. And some of them, enough energy gets added to them that they can break away completely from the other molecules, and they go into that vacuum that's above the fluid. And that's when they become a gas. Okay? So each step from solid to fluid to gas is an increase in the kinetic energy of the molecules, which leads them to more and more overcome those intermolecular forces until they finally escape those forces as a gas. What does that mean as a solid? Well, even within a phase, there's a change in the kinetic energy, right? So as you're heating that ice, it might move from negative 20 Celsius to negative 10 Celsius. It's got more increased energy. And what that leads to is that those molecules begin to push harder against intermolecular forces. They're not breaking them, but they're pushing harder against them. And that essentially makes your lattice expand, okay, because they're bouncing farther away from each other with their increased kinetic energy. The result is that a solid tends to expand as it warms up. And here's a picture of a bridge expansion device, which deals with this, right? You have a big bridge in the summer heat, the steel is gonna expand, and if you didn't have some sort of expansion device like this, the bridge would be in danger of buckling. But we have an equation that tells us how much it's going to expand, right? And so we have the length of an object, right? We have a change in temperature, and then we have an expansion coefficient here, and that has to do with the material, right? So if I have a steel frame bridge that's 100 meters long, and I know my coefficient of expansion, and then I think, well, the temperature might range from, negative 20 Celsius to 30 Celsius outside. Then I can figure out what range of length it's going to have, how much it's going to shrink in the wintertime, how much that bridge is going to expand in the summertime, and then I can build my bridge so they won't fall apart, which is always positive.